We had a question waiting on the Socrative app that reads, the line spectra, also called emission spectra, of the elements are what? To each other? Correct answer there, as we saw here the other day, they were all different from each other. And we often refer to them as the fingerprints of the elements because of their unique nature. We did then talk about some uses of the line spectra. These were some of them that we listed at the end of the hour. I don't think we wrote them down. One of the things that we failed to mention here at the end was somebody did talk about the composition of the stars, which is correct. But another thing that scientists know is that the universe is expanding, and it comes through the observation of what's called the Doppler effect. Now, how many have heard of Doppler before? Or where have you heard of it? Where has it been used? Weather, right. And so what the Doppler radar is used for is it helps track the movement of clouds and tells us where precipitation is and so forth. But I do have a short video clip here that talks a bit about the Doppler effect, and I did not see how our audio is tuned here, but we'll give it a shot and see how it comes out.
The Doppler effect. In Sheldon's words,
it's the apparent change in the frequency of a wave caused by relative motion between the source of the wave and the observer.
The Doppler effect is perhaps best explained visually. So here's a thing that is emitting waves. It could be a fire truck emitting sound, it could be a star emitting light, it could be a duck creating ripples on a pond. Those are all waves, and they all look something like this. We see the Doppler effect happening when the thing that is emitting waves moves. In the direction it's moving, the wavefronts bunch up, and behind it they spread out. If our object is moving towards a stationary observer, these bunched up waves are observed at a high frequency, and if the object is moving away from a stationary observer, the waves are observed at a lower frequency. So that is the Doppler effect, the apparent change in the frequency of a wave caused by relative motion between the source of the wave and the observer. It makes sense, but it gets interesting when you consider some of its applications. So let's say you are standing in the middle of a road. That's you, and the car drives past you very fast. As it does so, it honks its horn because you're standing in the middle of the road. The horn to you might sound something like this. So it starts at a high pitch and moves to a lower pitch, even though from the driver's perspective, the horn is playing the same pitch the entire time. So what's going on? As the vehicle's coming towards you, the sound waves that it's emitting bunch up, and so are delivered to you at a higher frequency, which you interpret as a higher pitch, because the frequency of sound waves is pitch. And then when the vehicle passes you and is moving away from you, the sound waves spread out, and so you hear them at a lower frequency, a lower pitch. So that's how the Doppler effect works with sound. It also affects another kind of wave, light. So let's say you look out your observatory and you see a star. Just like the car's sound waves, if the star is moving towards you, even just a little bit, the light waves that it emits will be bunched up, meaning that you see the light at a higher frequency than it actually is. Frequency in sound is pitch, so what does that mean for light? Well, if we look at our handy pocket electromagnetic spectrum chart, we'll see that a small change in frequency for visible light will change its color. Higher frequency light waves means bluer light, and lower frequency light waves means redder light. This is called redshift, and it may possibly be among the weirdest and coolest things of all time. Stars, or anything that you can see, change color depending on their relative motion to you. Of course, you can't see this minute difference with your eyes, but astronomers with the right equipment can use this effect to tell whether stars are moving away from or towards Earth. As it turns out, almost everything we can see in the universe is moving away from us very quickly, which is both an important piece of evidence for the Big Bang and an indication that the Earth might get very lonely in the distant future. Thanks for watching this video. Let me know if you got something out of it. Bye.
All right. So let's see what you learned from this video clip. Objects moving away from a stationary observer appear to have a what kind of wavelength to the stationary observer? Do they appear to have a shorter wavelength, a longer wavelength, or the same wavelength? Let's get our answers locked in, please. We'll count down. 5, 4, 3, 2, 1. And it is a longer wavelength. So again, if you want to think about this, if you want to just like scribble down a little diagram of some sort, you could maybe draw yourself, like I'm not an artist, and put in a little star. And again, if you think about an object that's stationary, you look at the waves like this. If that star starts moving away from the stationary observer, then those wavelengths get stretched out. And again, according to the video, we call that red shifting. It's the Doppler effect. The Doppler effect is what we observe, but in the case of stars, we call it a red shift, because what happens, in effect, is that, let's see, I have a little diagram on this one as well. So if we talk about the stars moving away from the Earth, if we increase the speed away from the Earth, you notice that as I'm increasing the speed here, this diagram or the spectrum of the star is shifting a little bit more to this red direction. Okay, and again, the phenomena is called redshift. Any questions? And when we look at most stars, when scientists look at most stars, we find out that most of the stars are moving away from us, which is where much of the idea of the Big Bang Theory comes around, where the thought is that the universe originated with a small mass that exploded in things then moving out away from us in all directions. All right. Now, when we looked at the line spectrum here the other day, we noticed that each element had its own distinct line spectrum. And we saw, for example, hydrogen had the 4 lines. Most of us saw the 3. Helium had a few more, and we saw neon. That was really cool. But the question here is, what is the origin of the line spectrum? In other words, how or why are they produced? And that should be they. So how or why are they, the line spectra, produced? And the reason was described, or at least credits given for the description, to a scientist by the name of Niels Bohr. And we refer to his model as the Bohr model. And Niels Bohr carried out some experiments. And here's how you spell his name. Carried out some experiments in about 1909. And in these experiments, or in his observations, he came to the conclusion that the energy of the electron was quantized. So the energy of the electron was quantized. And this means that the electrons were found in very specific orbits. Around the nucleus. So again, according to Niels Bohr, the energy of the electron was quantized. When we say that something is quantized, what that means is that only very certain, very specific values are allowed. One example could give is if we talk about your car traveling, for example. If the speed at which your car could travel was quantized, that might mean you could only travel at 10 miles an hour, or 20 miles an hour, or 30 miles an hour. You couldn't travel at any speed in between. And so if you went from 10 miles an hour to 20 miles an hour, you went from one speed to another instantaneously. There was no acceleration whatsoever. It instantaneously would change from one to another. And so again, when we talk about something being quantized, something that's quantized only has certain specific values, and other values aren't allowed. And here's how Bohr came about, and here's how we might envision this quantization. So this here is an example of the Bohr model, where again, when we look at the orbits in the atom, they might be these very specific distances from the nucleus. And again, all these figures are in your text. We're on page 292 and page 293 in your text if you want to look at these. But here's basically what would happen. First of all, let's say that I have this wood block right here. And this wood block can have different amounts of energy. I could hold this wood block up off the floor really high, or I could hold it down here on the ground. And depending upon its position, it has varying amounts of potential energy. So think about the position of the wood block. Think about it up here. Think about it down on the ground. And then ask yourself this question coming up. Which position of the wood block would have the highest state of potential energy? If I hold it up 6 feet off the ground, or if I hold it down on the ground? So which position do you think has the highest state of potential energy? And you get your answers locked in. We'll look at them and count down. 5, 4, 3, 2, 1. Correct answer is 6 feet off the ground. Because of course, if I drop it from this greater height, what happens as I drop it? And say compare it to dropping it from right here. Which one is hitting the ground with a greater force? Right, the 6 feet is going to hit it with a greater force. That's because at the higher position has a greater potential energy. Same reason why if you go see a dam, the dams that have the most powerful force are the dams that are built the highest or tallest. And so we try to get more energy out of them by building bigger or taller dams. So electrons are the same way, and the reason why potential energy exists is whenever we have an attraction between two objects. So in the case of this wood block and the floor, what is the force that's acting? Gravity, exactly. Gravity's acting on here. If we go to an atom, you might remember that in the construction of the atom, we have the nucleus. The nucleus has what type of charge? Positive. So the nucleus has a positive charge. The electrons that are sitting out here have a negative charge. So if you remember what we learned about charges, if they have opposite charges, the opposites will attract each other. Just like gravity will attract the earth and this block of wood. And so whenever we look at charged particles that have attraction for each other, the greater the distance between the electrons and the nucleus, the greater the potential energy. Okay, so there's going to be more potential energy when those electrons are further away, just like when we lift the block of wood up further off the ground, there'll be greater potential energy. And you might also consider an example like a couple magnets will have potential energy. You might notice that if you hold them close together, they'll want to like pop together. But if you hold them farther apart, if they're attracting each other, they're going to want to slam together real hard when they do so. So again, whenever you have a couple objects that sit in a field of force, the further those objects are apart from each other, the greater their potential energy. So ordinarily, now if I go back to this wood block, which state of potential energy would this wood block want to be in? Does it want to be in a higher state or in a lower state? Lower, because of course if I let go of the block, where does it go? Right, it goes down to the ground. And the only way to get it off the ground is to lift it up and put some energy into it to lift it up. Same is true with electrons and atoms. They ordinarily want to be in their state of lowest potential energy. So according to Bohr, that lowest state would be the first energy level. That is the one closest to the nucleus. And turns out that we have a name for that position. We refer to that position as the ground state. We refer to it as the ground state, just kind of like the wood block being on the ground. So again, we call it the ground state. And the ground state is the lowest state of potential energy. And ordinarily, electrons want to be in that ground state. But now, what can happen, just like we did here in class the other day, we pass some electricity through those gases. When we pass some electricity through those gases, we are adding some energy to them. So just like when I add energy to this wood block, I can bring it up to a higher state of potential energy. This wood block, though, is not stable in this higher state of potential energy, so if I let go of it, the block will return back down to a state of lower potential energy. So electrons are the same way. Again, ordinarily they'd want to be in the ground state, but if we put some energy into them, they'll go up to a higher energy state. But they're not stable at that higher energy state, so they wind up dropping back down to a lower energy state. And it's a continuous cycle that winds up occurring. As long as we're passing some electricity through them, they'll absorb some energy, they get lifted up to a high energy state. They're not stable there, so what will happen is they wind up dropping back down to a lower energy state. And it goes on and on and on. And the reason then why Bohr came to this conclusion that the energy of the electron was quantized was because if we look at something like hydrogen as an example, when you and I looked at it, the lines we saw in there, you might remember, we saw kind of a reddish line, we saw a bluish-green line, and we saw a violet line. And if we had really good eyesight, we might have seen one right down here on the edge of the visible spectrum, another violet line as well. And each one of those jumps corresponds to a different jump between these orbits in the atom. And so it turns out that when we observed the red line was a jump from the third level down to the second. The bluish-green line we saw was the jump from the fourth down to the second, and the violet one we saw was a jump from the fifth level down to the second. And you might say, well, what about jumps down to the first? Well, they occur. The difference is that the jumps down to the first are even larger jumps. And if they're even larger jumps, they have more energy. And it turns out that the larger the jump is, we wind up moving off of the visible spectrum. And so they actually are observed down here in the ultraviolet portion of the spectrum, which you and I can't see with our eyes. But we can detect it with other instruments. We can actually detect that those colors are, that those wavelengths are there. It's just not in the visible portion of the spectrum. And there's also jumps that occur, say, from the fourth down to the third, or the fifth to the fourth, the fifth to the third. But those jumps are going to be shorter jumps, and they're going to be out in this portion of the spectrum that we can't see as well. So there's a whole bunch of lines that are in there, but the only ones that you and I can see are the ones here that are in the visible portion of the spectrum. And so, one of the reasons then why elements have different line spectra, or we call emission spectra, is because they have different numbers of electrons, and each line that's in here corresponds to a different jump between the energy levels. But if we want to identify the elements, these lines stay the same all the time. And so if we wanted to heat up a gas and check to see which elements are in there, if we saw a pattern that had lines in these positions or these wavelengths, we could identify it definitely as helium. In fact, one of the interesting things about helium is that helium was the first element that was discovered somewhere other than the Earth. The first place that helium was discovered was in the sun. And helium was named after the Greek sun god, which is Helios. Okay? And so, in fact, if we start looking at all sorts of stars, we find out that the composition of stars isn't very interesting. The composition of stars is pretty much two elements, and those two elements are hydrogen and helium. Hydrogen and helium. And so, when we learn then that hydrogen and helium are the two elements that are the primary composition of stars, then it goes back to the fact that we can then look at distant stars and we know where we expect to see the spectrum of hydrogen and helium, but we see them that they don't fall exactly where they're supposed to be. We see that they're actually shifted over a little bit to the red side, which is telling us again that the universe is expanding because those stars are moving away from us, not moving towards us. Or that they're not static, because if they were static, we would expect to see those lines in the same place that we would see them for hydrogen and helium here, like we demoed them in class here the other day. So again, when electrons in their lowest state of potential energy, we call that the ground state. When the electron is not in the ground state, that is when it's in a state of higher potential energy, we refer to that as an excited state. So again, electrons that are in the lowest state of potential energy are said to be in a ground state. When they are not in the ground state, that means that they are in some state of higher potential energy. We refer to that as an excited state. Now, one of the really cool things about this, and one of the problems with the Bohr model, in fact, the Bohr model is not what we refer to today as the modern atomic theory. We've replaced the Bohr model with what we call the quantum mechanical model. And one of the biggest weaknesses of the Bohr model was soon identified. If we said that the energy electron was quantized, what that basically means is that the electron could only be in these levels and it couldn't be anywhere in between them. So when it dropped down to a lower energy level, it had to do so instantaneously. It couldn't exist anywhere in the middle. And so that type of jump or leap came up with a name, and that name was called a quantum leap. And how many have heard of quantum leaps before? And where have you heard it usually used? Sci-fi movies, exactly. And when they use it in sci-fi movies, what does it usually refer to? What happens when you do a quantum leap? Travel through space and time. You travel through space and time. And so the whole idea where this traveling through space and time comes from is the fact that when we talk about these quantum leaps, according to the Bohr model, these electrons could not exist anywhere in between. So if they had to do so instantaneously, it was like traveling in time. But when it's popularized in science fiction, we usually think about these huge jumps across space and time, when in reality, the term quantum leap originated from these jumps between the quantized energy levels in an atom. So that's kind of an interesting piece, again, associated with sci-fi. So the main problem then, and this was about 1909, one of the main problems with the Bohr model of the atom was this whole idea of the quantum leap. It didn't make sense. It's like, how in the world does this electron get from one level to another if it can exist anywhere in between? The other problem with the Bohr model was it only seemed to work well for the hydrogen atom. So when we're talking about the hydrogen atom, hydrogen is easy to deal with because hydrogen contains how many electrons? Just one. So as long as we're dealing with one electron, it works really, really well. And once we get to have more electrons in there, then the theory begins to break down. So scientists then kind of set off to see what we could do to make or give a better explanation for the line spectra. And these were some developments that came about in the 1920s. And in the 1920s, there was the work of 3 scientists. Now, we're not going to be responsible for names and dates in here. Just bring them up because A, your text mentions them, and B, to give credit where credit is due. And it's where we are today. And they were the work of these 3 scientists. There was Louis de Broglie. And de Broglie reasoned this. He said that when we look at light, as an example, light has a dual nature. And by a dual nature, what we mean is that light sometimes behaves like a wave, it sometimes behaves like a particle. Now, ordinarily, light has all of the properties that are associated with waves. And when waves interact with each other, whether the waves in an ocean or a mud puddle or sound waves, one of the ways they can interact is that they can wind up adding together. They can wind up canceling each other out. If you have noise cancellation headphones, that's exactly how it works. You basically, your headphones will pick up exterior noise and it's going to cancel them out by sending out the same waves it hears and pushing back against them, which in effect cancels those waves out. And so that's a wave property. All waves go through what we call reflection, and they go through refraction and diffraction. Those are some physics terms, but all of those are properties of waves. But light also has some particle-like properties, and if you have a calculator that has on it a solar panel. Your solar panel on here is making use of the particle property of light. And that is, whenever a particle of light strikes it, what it does, it hits the surface and it kicks out an electron. So as long as I expose it to light, electrons keep getting kicked out. And if it keeps getting kicked out fast enough, we eventually produce a current in there. And basically, an electric current is a flow of electrons. We can get enough power to power a calculator. Or if we see solar panels out elsewhere, those are just basically, every time light's striking it, they're kicking out electrons and producing a flow of electricity. So de Broglie reasoned that if light had this dual nature, he said then that electrons have a dual nature as well. So again, came to this conclusion that electrons have a dual nature. And that is that they sometimes behave like particles and sometimes behave like waves. So again, sometimes behave like a particle, and sometimes like a wave. And again, came to this idea by comparing light and saying, well, we've probably been looking at electrons the wrong way. We've probably been looking at electrons all along as if they are particles, but perhaps we should start looking at them like waves. And in fact, de Broglie was onto something. The electron microscope came about just a few years later with the whole idea that we basically, when we shoot electrons at particles or at matter, we can then find out how it interacts with matter and magnify images to a very large degree. Then there was another scientist, which some of you have probably heard of before, and it was Werner Heisenberg. And if I would have asked this question maybe 7, 8 years ago, nobody would have heard of Heisenberg, but how many have heard of Heisenberg? And where have you heard of him? Breaking Bad, sure. It was in the show Breaking Bad. And it was a code name that the lead character gave to himself. But Heisenberg is known for what's called the uncertainty principle. And it actually described the character of Walter White in Breaking Bad, because Heisenberg, or Walter White, behaved in a very uncertain or unpredictable pattern or characteristic. But here's what the Heisenberg uncertainty principle says. And we're not going to show this because mathematically the mathematics are too complex. It requires probably about 2 years of calculus. But what the mathematics showed is that it is impossible to simultaneously determine the speed and the location of an electron in an atom. If we learn something about its location, we'd know nothing about its speed. If we learn something about its speed, we'd know nothing about its location. Mathematically, we could not know the two at the same time. So when we talk about the Bohr model like this model is way too predictable. And so we cannot be that predictable about the speed and location of electrons in atoms. And then there was a third scientist with the name of Erwin Schrödinger. And Schrödinger worked about the same time as Heisenberg, and he treated electrons as waves. And came up with what's called what we call today is the Schrödinger wave equation. But in the Schrödinger wave equation, again, the mathematics are way beyond in here. Here's what the conclusions were of the Schrödinger wave equation. What it did is it defined orbitals rather than orbits. So it defined what we call orbitals rather than orbits to depict the locations of electrons in atoms. And we define an orbital like this. We define an orbital as being a region in space where there's a high probability of finding an electron. And so this kind of adopts the ideas of Heisenberg, where we don't know exactly where the electrons are located because we can't know their speed and location simultaneously, but rather we can talk about the probabilities of finding electrons in different locations. And so here's an example of what that means. So I'm going to take a couple figures here. And we'll start with this one here. We might look at a bicycle wheel. And a bicycle wheel would have a bunch of spokes on it. And if we would take that bicycle wheel and spin it around very rapidly, what would happen is that that bicycle wheel, the spokes in the bicycle wheel would fill up the volume. Now what we'd know is that there's a high probability of finding a spoke somewhere in the space. And I think I probably told you before, one of the things I used to do when I was a kid, we would take the bikes, we'd turn them upside down, we'd get the tires going really fast, and we'd throw rocks through them. And every now and again, as we threw rocks through them, we would find a spoke. Because again, there's a high probability of finding a spoke somewhere in that volume. So what this would be compared to would be a shape that looks something like this. This here would depict an orbital in an atom. This is an electron orbital with an atom that fills up a space. And when you look at this, the areas where you see it more densely shaded is the area where it's more probable of finding an electron. And areas where it is less densely shaded is an area where it is less probable to find an electron. So over here then, when we look at these models, these are all models of different orbitals. An orbital that has, or we show it more densely shaded here and less densely shaded here, would be depicted by a sphere. So this is, again, these are all examples of orbitals up here. Another analogy we might give is by plucking a string. And if we were to take a string and pluck it, that string would vibrate back and forth. And as it vibrates back and forth, it fills up that volume, and we could say it's probable to find that string somewhere in this space. Again, very similar to the shape of an orbital that we've shown right here. But sometimes when we pluck on that string, we might wind up observing something like this. That is, when we pluck on it, it might wind up filling up two different volumes. And we have what's called a small node right here. Now if you're a musician, and I know we have some in here, if we were to listen to these two, what would be the difference that we'd hear between these two vibration patterns? How does this one sound compared to this one up here? It'd be higher. And what does it mean by higher? Higher pitch, sure. Can you sing? No? All right. So I can't very well, but if I were to do it, if this one was da, da, boy, that was horrible. Da, da. All right. So that would be the difference when we talk about the pitch. Okay. So one has a higher pitch. And if we were to do the physics of it, we can also talk about them differing in wavelength. Which one of these has a different, shorter wavelength? Bottom one has a shorter wavelength, exactly. This one here is a longer wavelength, you can see. This one here is a shorter wavelength. But the shorter wavelength one has a greater frequency. This one here has a greater frequency. If we go back to pitch, the reason why we hear that higher pitch is because it has a greater frequency. There's a greater rate of vibration that's occurring. And it turns out that we'd say that the energy is inversely proportional to the wavelength. So energy is inversely proportional to the wavelength. And we can also say that the energy is directly proportional to the frequency. So again, energy is directly proportional to the frequency. Which means that if something happens, if this vibrates at a greater rate, it's able to produce more energy. So, it turns out that the energy of the electron depends on two different things. Energy of the electron depends upon two different things. So we would say, first of all, the energy of an electron depends on the size of the orbital. Depends on the size of the orbital. And we kind of already looked at that when we looked at the Bohr model. If we go back to the Bohr model and look at it, we want to think of these as orbits right here, or the orbitals. If on average it's closer to the nucleus, what can we say about its energy if it's closer to the nucleus compared to if it's further away? If it's close to the nucleus, we'd say its energy is a little bit smaller. If it's further away, on average, then its energy is going to be larger. Because remember, the further away the electron is from the nucleus, the greater its potential energy. So the greater the size of the orbitals, the greater the energy. But we also said that the energy is directly proportional to the frequency. So we could then also say that the energy of the electron depends on the shape of the orbital. The energy of an electron depends on the shape of the orbital. So if this vibrating string corresponded to an orbital look like this, then a string vibrating in this pattern would be like an orbital that has this shape right here. So this would be another shape. So we'd have two different shapes of orbitals. Again, this orbital would be like this one here. This orbital right here would be like this one here. So now if you look at these two orbitals and we say that the energy of the electron depends upon the shape of the orbital, which one is going to have more energy? Which one will have more energy? Well, let's go back to what we say up here. The energy of the electron is directly proportional to the frequency. So which one has a greater frequency? This one right here. And if this one has a greater frequency, this one should have more energy, because energy and frequency are directly proportional to each other. So what we say then is that the energy of the electron depends on two things. Again, they are the size of the orbital and they are the shapes of the orbitals. Yes?
How do you know that one has more high frequency?
It has to do with the shape. This has a low, it's just kind of like the, again going back to the vibrating strings. This one here has a very simple vibration. This one is more complex. The more complex it gets to be, the greater its frequency. Just like the more complex the shape of the orbital is, the greater its frequency or energy. And so as we go down this line then here and compare these two with each other, which of these two would have a greater energy? This one here as well. So again, the more complex the shape of the orbitals, the greater the energy of the orbitals. Now, each of these orbitals up here will hold up to 2 electrons. This orbital will hold up 2 electrons. This is a single orbital. This will hold up to 2 electrons. This orbital here will hold up to 2 electrons. So no matter what the shape is of the orbital, each orbital will hold up to 2 electrons. And one of the things we won't be doing here, if you look at the syllabus, it says that we're only covering about the first 4 or 5 sections of Chapter 9. If you had some chemistry before, you may have talked about electron configurations in there. If we talk about electron configurations, those have some application to what we might do in a more advanced chemistry class, but as an intro class here, we are not going to be dealing with electron configurations. So what would be sufficient for us to know then is this. What I'd like for you to know is that the energy electron depends upon the size of the orbitals, and it also depends upon the shape of the orbitals. Okay, any questions that you have? Any questions? Yes?
Is there a difference with like its orientation, like if it's pointing upwards or like sideways?
Okay, good question. The question is there any difference in terms of the orientation? In fact, that when we get in our more advanced chemistry classes, we talk about the orientation. When we name these orbitals, this is called an s orbital. These are called p orbitals. These are called d orbitals. And one of the things that you'll notice that if we are looking at these in 3 dimensions, all of the orbitals within 3-dimensional space do not actually overlap each other. So this one here is along the x-axis, this is along the y-axis, this is along the z-axis. And if you study these carefully, this here is on the xy plane, this here is on the xz plane, this is on the yz plane. And while this one here is on the xy plane and this one here is on the xy plane, notice that this one takes up the spaces between the axes, this one here occupies spaces along the axes. So in 3-dimensional space, they don't overlap any space either. And then this one here is kind of a hunky shape. This one comes up along the z-axis. There is a little disc that's in here, but it turns out that if we were to look at this plane right in here, this is actually probably not drawn correctly or to scale. There's probably like little holes that sit in here, and this little disc occupies that space in some holes that sit along these axes. So in terms of orientation, the one thing that you would get out of it, if we were to do it a little bit more advanced, is that within a what's called a sublevel, orbitals do not overlap the same space in 3 dimensions. But again, that's beyond what we're going to cover in here. Okay, Travis?
Does that have anything to do with string theory, or is that just coincidence?
Not entirely, no, it doesn't. Anybody else? Anybody else? Okay, so if I were to just quickly sum up what your expectations here are out of Chapter 9 and what you're not responsible for in Chapter 9, you are not responsible for electron configurations. And you are not responsible for orbital diagrams. I am fairly certain I tried to avoid assigning any problems on Master Chemistry associated with these. If I did, let me know, and we will get them removed from the problems. All right, so I have like, how many? 1, 2, probably about 5 questions here that come in a row. And these 5 questions, we'll kind of see what you've learned from what we've done here today. Feel free to talk with a neighbor on these. An electron that is in the first energy level, that is closest to the nucleus, is said to be in and we'll count down on this. 5, 4, 3, 2, 1. They're said to be in the ground state. Wonderful, great job. Next one. The Bohr model worked well with which element? It only worked well with which element? Count down. 5, 4, 3, 2, 1. Wonderful. First back-to-back hundreds all semester. The energy of an electron in an orbital depends upon which two characteristics? Energy of an electron in an orbital depends upon which two characteristics? Select both of the correct answers. And count down. 5, 4, 3, 2, 1. Size and shape, great. And then an electron in an orbital has the most energy if the size of the orbital is larger, smaller, medium-sized, or has nothing to do with energy. And count down. 5, 4, 3, 2, 1. That's right. If it's larger, remember that the larger it is, the further away it is from the nucleus, and the greater its potential energy. And then the last of these, an electron in an orbital has the most energy if the shape of an electron is get your answers locked in there, please. I'm passing out new periodic tables for everyone because we're going to be writing on these here today. I can pretty much guarantee you're going to see the last two questions on your next exam. So keep these in mind. We're going to count down on this one. We'll count down 5, 4, 3, 2, 1. And yeah, the more complex they are, once again, the more energy they have. So lower energy, simple shape, high energy, complex shape. And again, it has to do with these having a greater frequency. Think about the vibrating string. And the greater the frequency, frequency and energy are directly proportional. Any questions? Any questions? All right, that's chapter 9. We're going to move on to chapter 10. And when we go on to chapter 10 deals with chemical bonding. And we're going to look at our periodic table, and we might as well pull that out right now. I'll keep it out. And while we are not responsible for electron configurations in here, we are going to be responsible for what we call valence electrons. And valence electrons, these are going to be the electrons in the outermost energy level. These are going to be the electrons in the outermost energy level. And the way we tell the number of valence electrons will be based on its group number. And specifically, if we look at the Roman numerals for the A groups, which are the main groups. So this is the Roman numeral 1A, 2A, which means these elements have one valence electron. These have two valence electrons. We skip on over here to group 3A. These have 3, 4, 5, 6, 7, and 8 valence electrons, respectively. There's going to be one exception to all of that in the A groups, and that's one element. Which one element is an exception to that? It's going to be in group 8A. That element is going to be helium. Helium cannot have 8 valence electrons because it only has 2 electrons to begin with. Remember that the atomic number of 2 means it only has 2 electrons. So otherwise, for all of the A groups, the number of valence electrons is determined by its group number. Now, to represent valence electrons, we use what's called the Lewis dot formula. In fact, it goes by a number of different names. I'm going to write down some of these words here. Formula, structure, diagram, symbol, and the way this works, Lewis formulas go by about 20 different names. It's going to be some combination, usually, of a word from the first column, sometimes both. It's optional to include a word from the middle column and then one from the last column. So if we refer to something as a Lewis formula, a Lewis formula is the same as an electron dot structure, or a Lewis dot symbol, or a Lewis symbol. Okay, so all of those things refer to the same thing, and I don't know why we don't standardize the vocabulary on that, but I usually refer to it as the Lewis diagram. I'll use all of them, I guess. Right? So just understand that we're talking about the same thing when we use any combination of words from the first column and the last column. The middle column here is kind of an optional one, but they all refer to the same thing. So if you're wondering, even if you're looking at your author when your author's writing, it seems like not using consistent vocabulary, that's the reason why. But the Lewis dot structure looks something like this. If I use the letter X to represent a generic symbol, we then take that generic symbol and we surround it by dots. And the convention is this. We place one dot onto each side, and then we begin doubling up. So again, the convention is we place one dot on each side of the symbol, and then we begin to double up. And where we double up doesn't really matter. So for example, if we had 5 dots, 5 dots could look like this, or 5 dots could look like this, 5 could look like this. It could basically be any position as long as we're putting one dot on each side before we double up. If we're putting 5 dots on it, we would not do it like this because we're missing something here from the left-hand side. Okay, so this would be one that wouldn't work. But when we write out the Lewis symbol, the convention is we place one dot on each side before we begin doubling them up. So if we come back to the periodic table, all of these here have one valence electron. If that one valence electron would write a Lewis symbol with one dot. Elements in group 2A then would have 2 dots. Remember, now we're skipping over the transition elements and we go over to group 3A. Group 3A would have 3 dots. Again, where we place those 3 dots doesn't matter as long as we're placing one dot on each side before we double up. So now I'm showing the open side as on the right hand side. I can put it here and show the open side on the left. And that's the same as if we put the open side on the top. As long as we place one dot on each side before we double up, we're okay. Group 4A would have 4 dots. Group 5A would have 5 dots. Group 6A would have 6 dots. Group 7A, 7 dots. And group 8A would have 8 dots. With one exception. That one exception again would be helium. And helium would actually write it as He with 2 dots. And we'll be talking about this a little bit later. We do pair them up in helium. This is the one side where or we don't put one dot on one side, one dot on the other. It's because the first energy level only has a maximum of 2 electrons, and those electrons are paired up. So if we want to write a Lewis symbol for an element, the way that we'd write a Lewis symbol for an element, let's say we wanted to write it for something like nitrogen. If we want to write it for nitrogen, then what we do is we'd put the symbol N, and N would be surrounded by how many dots? I hear 7, I hear 5. What is it? 5 dots, because it's in group 5A. So put in 1, 2, 3, 4, 5. And again, where we double up doesn't matter, as long as we place 1 dot on each side before we double up. If we did something like boron, symbol B, boron would be surrounded by 3 dots. Good. So this would be the Lewis symbol for boron. So check what you learn here. This generic Lewis symbol would best represent which element? Which element in this list would best be represented by this generic Lewis symbol? Okay, and we'll get our answers locked in. We'll count down. 5, 4, 3, 2, 1. It's going to be sulfur, because sulfur is in group 6A. And sulfur being in group 6A would have 6 dots. And so again, come back here, we see sulfur right here under group 6A has 6 valence electrons. And if we had to write out the Lewis symbol for sulfur, we'd put in an S, and we'd surround the S with 6 dots. Just like that. Okay, any questions? Any questions? All right, last piece for today. I have some demos that we'll wrap up with. And this here is going to involve kind of an idea of how the periodic table developed. And the periodic table first developed in the 1860s and 1870s. And there's a Russian chemist by the name of Dmitry Mendeleev. And the time of Mendeleev, this was about 1869. There were about 50 known elements at the time. If you look at our periodic table today, the periodic table up on the wall shows 112 elements. The ones that we've passed out here have 118 elements. But again, at the time of Mendeleev, he knew of about 50 different elements. And at the time, there was some things known about how they interacted or reacted with each other. And what Mendeleev tried to do is he tried to organize that a little bit. So I'm going to demonstrate to you today the elements lithium, sodium, and potassium. And what I'm going to do here is I'm going to fill up these beakers, each with some water. And if you're disturbed by what you see in the water, the reason why it's so cloudy is because of, it's just air. This aerated line, there's an aerator that sits in here, and so there's just a little bit of air in the line. And to demonstrate this, I am going to put up an explosion screen. And I do it not because I anticipate there will be explosions. I do it just in case there will be. And I'm going to put this up here so you can see it on the dot cam. And try to get this centered. That looks pretty good. All right. And so the first one we're going to look at is going to be some lithium. And we'll go ahead and take the lithium out of here. All right. Now, in order to work with the lithium, you might notice first of all that it kind of looks just like a little chunk of metal, and that's really what it is. What I'm going to do is I'm going to take this piece of metal, and I'm going to take this blade right here, which you see is really dull, and I'm going to cut the metal with the blade. So we'll hold this into place. Oh, and if you're wondering what this liquid is here, this liquid is not water. This here is some mineral oil. And we store these in mineral oil because these are quite reactive with water vapor and air. And so by keeping them under mineral oil, we minimize their reactions. But you can see here now with this dull blade, we're able to cut off a piece of the lithium. And if you look at the surface here right now, you should be able to see some metallic luster that's on there. And I'm going to go ahead and put this back in the container, and we'll keep out this small piece. And then what I'm going to do, I forgot to check if I had any on my card. I do. I'm going to add some phenolphthalein. Now, I don't know if you've used phenolphthalein in the lab yet. Have you used? Does that sound familiar? Okay, phenolphthalein is an acid-base indicator. And it is colorless in acidic solutions and neutral solutions, and it has kind of a pink color in basic solutions. So right now it's either acidic or neutral, and since it's just water, I can tell you that it's neutral. I'm going to take this off of here, and we're going to put the water up now. And sometimes this reflection will cause the iris to close on the camera. Looks like it's not today. And so I'm going to take a piece of the lithium, and let's watch what happens when I put the lithium into the water. You might be able to hear the fizzing from back there, and you should be able to see the bubbles that are forming. And of course now you're seeing the pink color forming because it's becoming basic. Okay? But this is lithium metal reacting with water. Sometimes that mineral oil vaporizes, and that's what's causing me to cough up here. Okay, so again, that's lithium. And again, lithium was one of the 50 elements that was known to Mendeleev back in the late 1860s. I'm going to set this aside. And now I'm going to take out some sodium metal. And I don't have a whole lot of sodium in here, it looks like. I do have one good-sized chunk. And I want to put this on this other piece. And we'll take out the sodium. Again, we're going to use this dull blade wherever I put it. There we go. Now take note of what happens when I try slicing this one. Notice how easily it went through as compared to the lithium. I had to press a lot harder. This one is almost like cutting cold butter. This one went through pretty well. You can see once again when I cut it open, I have that metallic luster. I'm going to go ahead and place the sodium back into the container. And we'll set this off to the side. And just to show you that this is a reaction with water and not a reaction with the phenolphthalein that I added. I won't add any phenolphthalein this time. So I'm going to take a small piece of sodium, cut that off of here, and I'm going to try to zoom in just a little bit on this if I can. And watch what happens now. I have a kind of an odd shaped piece of sodium on the tip of this. I drop it in. Notice what happens to its shape. You see the shape of it? Turned into what shape? Sphere, right. And if I drop in another piece, see now they crash into each other and they form together. And the reason why they're the shape of a sphere is because this reaction is exothermic, which means it gives off heat energy. It's giving up enough heat such that it's caused the sodium to become molten, and that's molten sodium now that's dancing around on the surface of the water. And the whole reason for the explosion screen is this. I'll let this one finish reacting. There we go. The whole reason for the explosion screen is because of the reaction that's taking place here. And that reaction is, let's say in the case of lithium, lithium metal was reacting with H2O, liquid, and it was producing lithium hydroxide, which was aqueous, and some hydrogen gas. And what is the formula for hydrogen gas once again? H2. Now some of you may notice this as being a problem that you had on your last exam. Okay, and what you were supposed to do is to write out an equation for it and then balance it. If we balance it, we'd have a 2, 2, and 2. And this stuff over here, the lithium hydroxide, this is the basic material that causes the solution to turn pink. And the only thing that was different this time is I substituted lithium with sodium. And when I substitute with sodium, then the product on the other side would have been sodium hydroxide. And then the last one I'm going to do is going to be potassium. And potassium would react with water to produce potassium hydroxide. So again, we just get rid of the lithium, we replace it with one of the other ones. And again, it'll be basic. Now I didn't add the phenolphthalein to this one here before, but if I did, add it now, what should happen to it? It should turn pink, right. And if I do this one that I haven't reacted yet, we'd see that this one here still is the colorless solution. Now, the reason for the explosion screen is because of the presence of hydrogen gas. And because I produced this as a molten metal, that hydrogen could wind up igniting. The hydrogen ignites, then what could happen is that that molten sodium could splatter. And if you see a few of these spots on the screen here, it's probably some of the molten sodium that is splattered out from previous times that this one has been done. So I'm going to wrap up with looking at this one here. This one is potassium, and we'll get this back up on the screen for you to look at. There we go. And we'll go ahead and take this one and get a nice chunk off of here. Now watch how easily this one slices. I mean, this one is just literally like slicing butter. I mean, it comes right off there very quickly. So if we're noticing a trend right now with the metals of group 1, what's happened to the softness as we've gone down the group? It becomes softer and softer, right. And let's notice what happens to the reactions. We saw what happened with the lithium in water. Next we looked at sodium in water. And again, now this one we're going to look at potassium in water. So I'm going to cut off a piece here. I'll bring the potassium hydroxide up here on top. And to make this one a little more interesting, we'll turn down the lights a bit. And we'll turn on more lights. I need to see a little bit here, but we'll pop this in here. And we see now this one here, the potassium metal actually ignites in the water. And again, that's the whole reason for the explosion screen. It's just in case this ignites, we don't want it to splatter out. And all right. So then as we go down the periodic table, not only did we see things get softer, the metals get softer, but what else happened? What happened to the reaction rate? The reaction rate increased. They became more and more vigorous. So if we went down the line, what would we expect to see with rubidium? Softer and faster still, and then we get down to cesium, still softer and a lot faster. So I got about 3 minutes left here. I got to tell you a couple stories. One of them, this was one that happened to me when I was in graduate school. I was hired to do a job and went into an old chemical stockroom, and chemical stockroom had chemicals that were going back to the 1920s and 30s and whatever else. And having sat in this old stockroom, a lot of these labels over the years had begun to fall off and everything. So they came to those graduate students and they said, well, we need you to identify what these chemicals are because we need to make sure that these get disposed of in an environmentally sound manner. And so as we're going through them, we came to this jar, and in this jar there was a bunch of white sticks. And on the outside of the jar, somebody had written the letter P. So being the bright chemists we are, we look at the periodic table and we see P, which of course is phosphorus. We look up the disposal procedure for phosphorus. It says, place sticks underwater and sent into crude landfill. So we took these white sticks, which we thought were P, we placed them into the water, and after they sat for a while, things started to flake off and all of a sudden started to bubble. We knew we were in trouble really quick. One of my friends had the presence of mind to throw down the explosion screen. Instant threw the explosion screen down, the thing exploded in the hood and cracked. I mean, we're talking like bulletproof explosion screen, probably like half inch. And we learned real quick we weren't dealing with P, but we were likely dealing with K. And so I always say there's a moral to this story, and that is it's always important to mind your P's and K's. All right. So yes, pay attention to your symbols. Somebody mislabeled that one. The other one was my very first teaching job out of high school grad school was at a high school down in southern Minnesota, down in Owatonna. And I taught 9th grade science that first year. And there's one of my buddies who was doing the same demonstrations, except we did not have potassium, he only had lithium and sodium. And the sodium there came in some pretty big chunks. And so you saw me dealing with like little pebble size. These were like rock size chunks of sodium. And one of his students got quite fascinated by the sodium and I wonder what would happen if I would throw the sodium out in the snowbank. Okay, so he snuck into the stockroom and stole a chunk of sodium and put it in his pocket. Now the thing is, when you are being really devious, you start sweating a lot, right? And you put the sodium in your pocket, you've got sweat, it starts reacting in your pocket. And turns out that when it reacts with the water, it winds up forming sodium hydroxide. And sodium hydroxide is commonly known as lye. Remember, it's basic. The same stuff used in drain cleaners. Started burning his skin. So he went to the place where all little boys go to dispose of evidence, went to the toilet, threw it in the toilet and blew the toilet bowl apart. So that was kind of an interesting little thing. I'm going to throw up on, in fact, I think it's already up there. If you go into D2L, I did post a video where they actually disposed of, I think, 47,000 pounds of sodium into a lake in Washington back in the 1940s, before they thought of the environment. Take a look at that. It's called Lake Lenore. You'll see it up there at the class.